All right, hey you guys, today we are going to be talking about forces. This is one of my favorite things that we cover in all of physics, all right? So, what is a force? Well, a force is a push or a pull, okay? So, I am pushing this drink across the table or I'm pulling it. That means there's a force there. It also acts on an object. So this bottle would be the object. It requires something to exert the power. So that would be me exerting it. It is a vector because you'll notice it has direction, doesn't it? It also has a magnitude. And it can be either contact or long range. So this would be a contact force. I'm touching it. Long range would be something like, well, if you jumped out of a plane to go skydiving, wouldn't you fall towards the ground? Yeah, you would. However, there's not a contact force that's pulling you down. What's pulling you down is gravity, and gravity is considered a long range force. It means it's not touching you, okay? Now, there's a few steps when it comes to drawing vectors, all right? The first step is we're going to model the object as a particle. So let's just keep talking about this, because I could even apply force this way. Whatever. We'll make the bottle an object, okay? So when it says to model it as a particle, it means that you can just make it a dot, or I really like to make them little boxes, personally. So little boxes are going to be what you mainly see me using in class. So this box is my particle, okay? The second thing is to place the tail of the vector on the particle. Remember, the tail is the part that doesn't have an arrow. So if this is my object and I'm pushing it that way, that means my arrow is going to come off of this and it's going to go that way, okay? So this is my tail, this is my tip. The tip has the arrow. The third step is to draw the force vector as an arrow. Look, I already did that. Pointing in the proper direction with the length proportional to the size of the force. So this would be like maybe a medium-sized force. Something like this, that would mean there was a smaller force acting on it. And something like this would mean that there was a much bigger force acting on it. So the length of the line is going to matter. So like maybe this was 1, this was 5, and this was like 15, okay? The other part is to give the vector an appropriate label. So if I'm pushing that, I could just label this F vector. So whatever you label it needs to have an arrow above it, okay? So let's do a couple of examples together, all right? The first thing we're going to think about is if we have a box and we have someone over here who is pulling on a rope that is attached to a box, all right? Well, first things first, we're going to recognize that the rope is that agent that's acting on it. Remember how here I was the agent acting on it? Now the rope is the agent. But we want to draw the vector. So here's our object, right? And then we're pulling it to the right, okay? So that's going to be our vector for that. Then what if we had a spring on the wall and we had a box connected to it? Well, now the agent that's acting on it is going to be the spring, okay? And what this would look like is, once again, the spring is pushing out, so it is creating a force outwards. We'll call this previous one we did the force of the rope, and we'll call this one the force of the spring, okay? So they're labeled, they're there. Then what if we have a box that's in free fall? It's just falling down to the earth. Well, if we drew the vector on that, it would just be coming down. And that's going to be due to the force of gravity. Okay? Now, you'll notice that at every single one of these, like I said, the tip is pointing away, okay? You will never, and I mean never, draw a vector where the point or the tip is going into the object. We do not do that. That is not allowed. I will cry at night if you do that, okay? Don't do it. Now that we looked at that, let's talk about combining forces, okay? So, what do we do if there's a bunch of different things acting on an object? So let's say maybe we have a box. Again, love boxes, okay? We've got one person pulling it this way. We've got one person pulling it this way. Well, there's two forces. So what are we gonna do? Well, thankfully, since we're already doing this on a box, it's like we've already drawn our vectors, right? We just got to add those little arrows. And we need to know what the force is overall acting on this object. So we'll say this is force 1 and this is force 2. What we are going to call the combination of these forces is F net, okay? And what F net is defined as is the sum, all right, the sum of all the forces from 1 to n. I don't like how that looks. I try to avoid the little summation sign at all costs. So all that's really saying is you would add force 1 plus force 2 plus force 3, and so on and so forth until you get to whatever that last force is. Okay? So if we were doing that on this one, but we don't have any numbers, we just want to see like, well, what is F net even going to look like? If we have something acting down and we have something acting this direction, wouldn't it be fair to say that our force is probably, our F net is going to be somewhere over here, right? Because if you got one person pulling you one way and another person pulling you the other way, those are going to combine and they're going to pull you a completely different way than those two separate people are pulling you. So that would be the F net on the box, which would just be equal to force 1 plus force 2. And that's just adding vectors. You guys are pros at adding vectors by now. So you're going to love this, right? So let's talk about some of the forces that exist. There is a list of this for you in the PDF. So I'm not just talking at you. You do have the information. I just don't want to write it on the board, okay? First one, gravity. We already talked about it. It's long range, right? It's not touching you. The other really cool thing about gravity is that it's always vertically downward. So if you're a box and you're falling, it's vertically downward. If you are on a ramp, oh, it doesn't matter. Your gravity is still just going to be pointing straight down. If you're on the moon, will it be pointing towards the earth? Okay. So it's always going to be pointing straight down. How do you think we're being held up? We have gravity acting on us straight down, okay? The next thing is the spring force. So let's look at this. We have a spring attached, okay? And then we have another one that has a spring attached. Well, those springs look different, don't they? So you know it talks about how a force is a push or a pull? Well, in springs, there's different ways you can have a push or a pull. Right here, it's compressed. And have you ever played with a spring or a slinky? Or have you ever had one of those little springs and your pin pop out? Okay, that's because when the spring's compressed, it wants to push. Okay, so this is a compressed spring, and the compressed spring wants to push. Now, what happens when you're playing with a spring, or if you've ever played with a slinky, and it gets really long and then you let go? Well, it pulls itself back right? So when the spring is stretched like this, it's going to be a pull. So when it's all close together, it's a push because it wants to push out. And then when it's all far apart, it wants to pull back in, okay? So compressed spring and stretched spring. After that, we have tension forces, okay? Tension would be sort of like, let's say you're sitting down and you're fishing for the day, all right? Well, you have this that comes over, right? Your fishing line. And then, well, you're in luck. A big old fish is going to come along and it's going to bite it. And I know that's a horrible fish. I'm so sorry. It's a new species, okay? It's going to bite it. And when it bites it, you're going to pull back. And when you pull back, what happens to the fishing line? Well, what happens to the fishing line is it gets really tense, right? It's tension that's causing it. So this right here would be a tension force. All right, tension. Tension is always in the direction that the string or rope is in. So you'll notice that the string or rope is going that way where he's pulling it, so it's creating the tension on the string when you're pulling up on that fish. Okay, normal force is another really cool thing. You know how I was talking about the fact that gravity is sort of holding us here? Well, what's making it so that gravity doesn't pull us completely through the floor? What's making it so that my laptop that I'm recording this on right now isn't falling through my podium? Well, that is called normal force. Normal force is always going to be perpendicular, okay? Now what that means is it's always going to make a right angle with the surface. So if we're on a flat surface, well, this is going to be our normal force. If we're on a ramp, well, perpendicular, this is going to be our normal force. Normal force is going to be what holds something in place, what holds you up. Like when you don't fall through your seat, when you're sitting in my classroom, what's holding you up? Normal force. It pushes up as gravity pulls down. Okay, another thing is friction. So let's talk about this. When I have this bottle and if I just push it, what eventually happens? It stops, doesn't it? Well, something has to be causing that because if I push it, it should just go on forever, right? No, friction is a thing. If you take your hands and you rub them together, what happens? They get hot. Why do they get hot? Well, you're creating friction and enough friction is going to create heat. So let's say this is my bottle, all right? And I just pushed it that direction. Well, the friction is acting here on the ground and it's pulling it back. It's trying to stop it. So I've got a force of friction over here when this is just sort of the force that I applied to the bottle. But there's a force trying to stop it, okay? There are two different kinds of friction. There's static and kinetic. Don't worry about those right now. We are not there yet, but I still want to make sure that you are aware of friction and that it exists. Okay, so you might be wondering, well, is that all of them? No, there's always more forces, okay? So drag. Drag is going to be the opposite of the motion. So you know how we were talking about skydiving, or let's say we have our box again, and we said that gravity was acting down on it, pulling it back to the earth, right? Well, if you've ever fallen or if you've ever skydived or done anything really like that, you'll notice that as you're falling, you feel something, right? Something's pushing up on you. Or you've seen a skydiver and they let out their huge parachute, right? And then the parachute doesn't just flop there. The parachute gets filled with air and it's what brings them down slower. What that is drag, okay? So drag is going to push up. Sort of like air resistance, because you guys have mentioned that word a few times already. So that's drag. It's opposing the motion, okay? Because the motion is to come down, but drag is saying, no, I don't want you to go quite that fast on your way down. The final one we're going to talk about is thrust. Thrust is specific to a jet or rocket engine. When it expels molecules at high speed, okay? Now, what to think of when you think of this is, imagine you've got your little rocket. Have you guys ever seen a rocket blast off? It creates all this stuff, right? You see a big explosion, okay? This is our thrust. And when a rocket does that, is the thrust making it go deep into the earth? No, the thrust is making it go up, up, up and away, up into the sky. So thrust is going to be this way, and this is going to be our force of thrust, okay? Now, that is our catalog of forces. Are we going to talk about all of them right away and use all of them right away? No, we're going to take little baby steps, but I just get so excited about all the different kinds of forces. I just had to tell you about them, okay? Where we're going to go from here is, well, how do we actually identify our forces when we're given a problem? Because as you guys have told me that you hate on multiple occasions, physics is just all word problems, right? So how do you identify what your forces are when you're reading that word problem, okay? So the first step is to identify an object of interest, like my bottle here, okay? And then to draw a picture of the situation. So this is my desk. I'll make my bottle look more like a bottle. This is my bottle. So I drew a picture of the situation. Now I need to draw a closed curve around the object. Okay. Closed curve around the object. And just for flair here, I'm going to say that I've got a rope attached to it that I'm pulling from, okay? Then locate every point on the boundary of this curve where other objects touch the point of interest. Okay, so I have a rope that is touching my bottle. I also have this table that is touching my bottle. So I've located those. Name and label each force acting on the object. All right, so if I've got a rope here that's pulling on it, that's going to be my tension force, okay? And then, well, it's sitting on a table, so I have gravity acting on it, and I have a normal force, right? And then also, if it's getting pulled across the table, there's also going to be a friction force at work on it, okay? So I've named and labeled the contact forces. Well, the second part was to name and label the long range. And well, I just went ahead of myself and I labeled gravity because I just get too excited when we talk about forces and Newton's laws and all of that. So this would be everything I have acting on my object. But now, just for extra practice, I want to draw a free body diagram. So here's my bottle. Here is my friction of tension. Here is the gravity acting on it, the force of gravity. Here we can see that normal force. And then here we would put that force of friction. All right. You might be wondering why some of these are on the outside of the box and some of them are on the inside. Well, that's because gravity acts on something from its center of mass. So the center of mass of a box is going to be the center of the box, right? And then normal force acts from the object that it's on. So I always like to draw that coming from the bottom up. It just brings the concepts to a whole new level, and I love it. All right. There are a few examples in your notes for you to look at that help to break down those steps again. We have a bungee jumper who has leapt off a bridge and is nearing the bottom of her fall. We have a guy skiing who is being towed up a snow-covered hill by a tow rope. And we have a rocket being launched into a new satellite. Well, to place a new satellite in orbit. So we'll look at the skier and the drag. So here is my skier, and I know what you're thinking. She's such a gifted artist. I really appreciate it, you guys. So get him pulled up. We're gonna draw this around. The first thing I notice is we have tension. All right, then, and I'm just gonna go ahead and label him like he's a free body diagram. Then I'm going to think about, well, what else is contact? Well, he has maybe the force of friction acting on him. He's on snow, not ice. All right. Then he also has the contact of his normal force, right? He's got that normal force. And then finally, his long range one would be that he has the force of gravity acting on him. So there is our skier's free body diagram off of his body. And then we'll go ahead and look at the rocket, okay? So we've got a rocket, and it is being launched up into space. It's got all this stuff coming out, okay? Well, what's acting on the rocket? We have gravity acting on the rocket, and we have thrust acting on the rocket. But have you guys ever heard about how, like, when they're going up into space, they have to break through, and there's like all of this like fire that's coming down, there's a possibility of debris and big explosions and all that stuff? That's because it's also experiencing the force of drag, okay? So it's experiencing gravity, thrust, and drag, but if it keeps on going up, which one is winning? The thrust is winning, okay? The thrust is winning. So, what exactly do forces really do? That is a valid question. So, give me a second. I'll be right back. I'm going to run and get a rubber band. All right, you guys, I'm back. So, when you have a rubber band and you go in and you want to stretch that rubber band, all right? It has a specific force assigned to it. Anytime that it is stretched this much, it'll have the same force, all right? No matter if, let's say, I attach 1 inch to my drink here and I take it to the same stretched level, it still has the same force on it, okay? But what I want you to think about, what if I had 2 of these rubber bands and then I pulled them both? How much force would be going on? Also, what kind of force is this? Because watch, when I let go, woo, they go back together. So, all right. So it's almost as if it were stretched out and then it compressed back together, right? So if an object that was pulled with a constant force, that means it's also moving with a constant acceleration, all right? So constant force means constant acceleration. And then we've talked about mass sum. Remember, we've been using grams or kilograms, and you guys had to convert and you hated it. Well, mass is also really important in forces when we're talking about these things called Newton's laws, okay? And what mass means here is that an object has inertia. And you might be thinking, what does inertia mean? Well, what inertia means is it's the object's resistance to changing its velocity or its resistance to acceleration. So in general, you can think about it as it's an object's resistance to change. The object doesn't want to change. So for instance, this has inertia, right? Because it has mass, but it's not super resistant to change because it's really light. However, this desk, oh, it's heavy. It's super resistant to change. Oh my God, I can't move it. All right, so this desk has a lot of inertia, whereas this, barely. It'll just move wherever I want it to. Hopefully that doesn't explode on me when I go to drink it. Okay, now, what I'm gonna leave you with until next time though, is Newton has some laws, right? There are 3, okay? And the second one is actually the first one we're going to talk about. And it's basically just that our net force is going to be equal to the mass times its acceleration. So F net equals mass times acceleration. Or as I like to say it, F equals ma. FMA? Maybe it'll catch on, maybe not. So we'll try to do a little bit of practice with all the stuff we learned tomorrow, and it's going to be like light practice, okay? It's not going to be anything insane. We haven't fully talked about this law yet. I might ask you to use it a couple times, but if anything, you should be able to do it, because let's say we want to solve for m. Well, we're just going to divide both sides by a, right? Okay, let's say we want to solve for a. We would just divide both sides by m. You guys know how to rearrange equations, right? I think you do. So all Newton's second law is that force is equal to the mass times the acceleration. And we will get into that more in your next video. We'll talk about that. We'll talk about Newton's first law. Who knows? If we're feeling crazy, maybe we'll just go straight to the third. But yeah, I love Newton's laws. I hope you guys love Newton's laws. It's seriously one of my favorite parts about physics. Always has been, always will be. I hope you guys have a great day, and I will see you tomorrow.